So now uh, Filippo will present to us about electromagnetic energy extraction from black holes.
Thank you. Yeah, I'm like one of those old enemies in movies. You will never get rid of me. Uh, and we still talk about the same topics, actually, which is electromagnetic energy extraction from black holes. And it's mainly based on these three pretty much recent papers. One of them is actually very recent, and it will be the one that I will be focusing on. Um, well, I guess we can skip this animation, but you know this story already. So we can extract energy from black holes by injecting negative energy. One of the most realistic astrophysical scenario in this perspective, in terms of generalized Penrose process, is the Blunt-Forest-Nayak mechanism. We will see something about this, and there's also another interesting process that was recently proposed, and which exploits a process occurring in resistive plasma, which is called magnetic reconnection, and I will address in the last part of this talk. So to test this hypothesis, we recently performed a number of numerical simulations by exploiting a new code that was developed in Frankfurt. It's called the Frankfurt Particle in Cell Code for Black Hole Spacetimes. It's a particle in cell code, so it is a code which allows us to evolve the dynamics of a large number of particles. We have pretty much 1 billion of particles around the black hole. These are charged particles which mimics the dynamics of a pair plasma, so electrons and positrons, and we can also evolve strong electromagnetic fields around the black hole by following the equations that I showed you before, basically. We performed a number of numerical simulation by varying the black hole spin, and the idea is to trying to understand what is the spin dependence in this mechanism. Okay, the spin dependence in this energy extraction process. Here you can see an example for one of these simulations, which basically represent a black hole magnetosphere. So here on the left, in terms of the plasma density, and on the right, in terms of the particle Lorentz factor. But if we want to understand this image, if we want to understand what we are looking for, it's better to resort to some analytic considerations. And well, we know already something about this. So, of course, we are talking about a black hole magnetosphere. So, the regime that we are trying to simulate with this code is that of force-free electrodynamics. In this case, the field should be described by this expression in terms of the magnetic flux, which is constant along these white lines, the poloidal current, and the angular velocity of the field lines. We have seen before. Now we can wonder what are the other surfaces which are highlighted in this picture, and to do that we can try to analyze the field motion. So what we can do is to take an observer which is co-moving together with the magnetic field lines. This will rotate around the black hole, so we can consider an observer moving with a circular orbit. So it's a co-rotating observer with an angular velocity which is exactly the same of the field line's angular velocity. Of course, you want this observer to be normalized to -1 because it has to be time-like, and you derive an expression for the normalization factor f. Actually, it turns out that this f is a quantity that can also be vanishing, meaning that a physical observer with this property cannot exist. And the reason why it cannot exist is that when this function turns out to be vanishing, the field line are co-rotating with a superluminal rotation. So observers which are on the surface where the function vanish, which are called the light surfaces, we have seen them before, will not be able to simply co-rotate together with the field lines and will start a radial motion. Also, we have two light surfaces. One is an inner one, always inside the ergosphere. The other one is an outer one. It's also interesting, since we can do it with this type of kinetic simulations. This is something we cannot do analytically because in force-free electrodynamics, the informations about the plasma are not relevant because the only dynamical quantity is the field. So it is interesting to understand the plasma motion. And we can actually constrain the form of this plasma motion by means of the expression that I showed you before. In particular, we have a component which is given by the drift, the so-called drift velocity. And basically, we have one point in this image where the radial motion is vanishing. This is called the stagnation surface, and it is represented by this red surface here. So let's go ahead. It's important to compare the numerical results with the analytic one. So you already know the procedure is the analytic one is a perturbative procedure. So we perturb around the split monopole magnetosphere, and the price to pay for splitting for reversal is that of creating a current sheet, which is precisely another feature that we observe in our simulation. So once we have the perturbative expression, we can solve the equations of motions, we can derive the expression for the Blunt-Ferrers-Nayek power, and actually the story is not that simple at that point. I skipped this part in the lecture. But the point is that the perturbation theory breaks down at the position of the outer light surface, because the outer light surface scales in a non-perturbative manner with the black hole spin A. So what you need to do is to enhance the perturbative approach with a matched asymptotic expansion scheme. So you have to introduce a new radial coordinate, r bar, in such a way that you basically split the space-time around the black hole in two different regions. In one region, everything works in the same manner as we already discussed. So you perturb the field variables and so on. In the r bar region, instead, we have to use the radial coordinate r bar, which is the proper one to keep the position of the outer light surface fixed in this perturbative approach. And since the scaling of the r bar coordinate is different in A, we will also have a different perturbative expansion. Now, the two perturbative expansion have to match each other, and this is the essence of the matched asymptotic expansion scheme. So you can see in the colors the terms which are matching at each order in the perturbation theory. This allows us to derive the final result of our matched asymptotic expansion analysis, which is an expression for the Blunt-Ferrers-Nayek mechanism at higher orders. And once we have this, we can make a comparison. So I highlighted in read the terms that were added first by means of this method and were previously not discussed in the literature. Once we have this, I will skip some part. Once we have this, we can make a comparison with the numerics. And as you can see, the black points are those predicted by our simulations, and there is basically a perfect agreement between the two. So the tendency is perfectly reproduced. The only caveat is that in order to fit this data, we had to change the magnetic field geometry coefficient kappa, which is solidly associated to the magnetic field geometry. And the reason we had to do that, to us, is pretty clear, because there is something clearly unstable in our numerical simulation, which is occurring at the position of the current sheet. This instability is precisely caused by magnetic reconnection. So magnetic reconnection is something that occurs whenever we have two magnetic field lines with opposite polarities, which are very close to each other. They can make contact in this reconnection X-point configuration, and if this happens, we can have a sudden rearrangement in the topology of the magnetic field lines, which will occur at the expenses of the energy that they store, which is converted in the kinetic and thermal energy of two oppositely directed plasma outflows. in the final stage of this highly nonlinear process, what we observe is that magnetic reconnection is mediated by coherent plasma structures, which are these blobs of plasma that you can observe here in our simulation. These are called plasmoids and are supposed to be some effect related to the flares that, for instance, we observe around Sagittarius A star. So it seems that the dynamics of these plasmoids is quite relevant for black hole magnetospheres. And it's precisely these plasmoids which are supposed to be some sort of new channel for a new type of Penrose process. So the idea is that in some part within the ergosphere of the black hole, we have magnetic reconnection that occurs. Two plasmoids are being ejected, one with negative energy falls into the horizon, the other with positive energy escape at infinity. So it's pretty much like the original version of the Penrose process. We have studied this mechanism analytically, and we have found that in principle it is possible for this to happen if the black hole is sufficiently spinning, so we are above this critical point, and if the magnetosphere is sufficiently magnetized. In this case, it is possible to extract, by means of this mechanism, some consistent power fraction of the Blanford-Znayak power. And our numerical simulation seems to support, in a sense, this idea, because we can look at this space-time diagram where the peaks here in the density represent the world lines of plasmoids. And it's kind of interesting to notice these 2 points where we have that within the ergosphere, we have 2 plasmoids being ejected, one in 2 opposite directions. Well, now, interestingly, these 2 points precisely corresponds to points where we have a transition for the energy of the particles from negative to positive energy, or vice versa. And having negative energy at infinity is one of the necessary conditions for a Penrose process to occur. So we have some promising result about this. And here is my conclusion, is some outline for this talk. Thank you for the attention.
So, do we have questions? Right. So, I'm always, when I see those very complex simulations, I'm always curious in which framework these simulations are done, because I'm aware of, for instance, Einstein toolkits. And do you know what kind of? Because as far as I know, you do the analytical part of the.
Yeah, I'm mostly an analytic guy, as you know, but I like this code was developed by Claudio Meringolo in Frankfurt am Main. He developed it by scratch, let's say. The code is actually based on other flat space-time particle in cell codes. But he generalized it, he managed to generalize it to curved space-time. And yeah, so there is no pre-infrastructure for the moment. Like it's gonna be released at some point.
Right. So there, sorry, there is no open source way of.
No, not
Doing
for
any
the
of this.
moment. There is some, like online, you can find free versions of the code, which of particle in cell codes, which work in flat space-time. I think that there is some group by Washington that recently made an open source code for GR-peak. So that I think is open source. And yeah, I didn't contribute to write the code. My main contribution is to understand what kind of initial condition put in this if we want to have this sort of situation, and to analyze the data pretty much.
Thank you. So, if there's not any further question, let's thank Filippo once again.